Now let's talk about the rank of a matrix. And this is covered in section 10.5.1 of the textbook. After viewing this video, you'll be able to quickly determine the rank of a matrix, or relatively quickly determine the rank of a matrix, and explain how the rank pertains to the dimensionality of the row and column space of the matrix. So before we define what a rank is, well, I guess let me write down the topic. Before we define the rank of a matrix, we need to I need to introduce what a submatrix is. And a submatrix is any matrix formed by removing at most m-1 rows and n-1 columns. And that's from a m by n matrix. So consider the matrix A, which is a 2 by 2 matrix in this example. This has 9 submatrices. So there's one 2 by 2 matrix, or submatrix, and uh, this is itself, basically. So a matrix is also a submatrix of itself. There are two 2 by 1s, 2 rows and 1 column, so we can remove the first column and get this 2 by 1 submatrix, and we could remove the second column and get the second 2 by 1 matrix. And that would be A11 would be 1 2 by 1 matrix, A21, and the second would be A12, A22. There are also two 1 by 2 matrices, submatrices, A11, A12, as well as A21, A22. And there are also four 1 by 1 submatrices for a total of 9. So now that we've talked about submatrices, we can define rank. Rank is defined according to the following. So the rank of A, which we can write as R parentheses A, is the dimension of the largest R by R matrix, so it's a square matrix, with a non-zero determinant. And I should also say that a zero matrix i.e. one with all zeros, has a rank of 0. So again, the rank of A is the dimension of the largest R by R square matrix with non-zero determinant. So if A, for example, were a column vector of 5, 6, and 0, the largest square matrix that it can form is 1. And so the rank of A here is also equal to 1. If we have a matrix that's 3 rows, 2 columns, for example, 0 on the first row, 3, 2 on the second row, and 1, 1 on the second row, you can see that um, the largest square matrix possible is 2 by 2. And so if we were to look at this upper submatrix right here, we could see right away that the determinant is equal to 0. So that would be that would not have a non-zero determinant. But if we looked at the second submatrix below, the determinant here is non-zero. So the largest R by R submatrix with non-zero determinant has dimension 2. So the rank of B here is equal to 2. And if we had another matrix, say a 3 by 3 matrix, the rank of this matrix is also equal to 2. And we could check that, but we would want to know if this has a rank of 3, because it itself is a 3 by 3 square matrix. But if we took the determinant of C, we would find that it is 0. And so the largest possible subdeterminant is not itself, but it happens to be a 2 by 2 submatrix. That's the largest possible submatrix that has a non-zero determinant. So those are 3 examples. And now I'd like to discuss theorem 10.5.1. And that theorem states that elementary row operations do not alter the rank of the matrix. So that means that a matrix formed by Gauss elimination has the same rank as the original starting matrix. For example, let's look at the following matrix. So we start with a 3 by 3 matrix. And if we go through Gauss elimination, and remember, Gauss elimination was the case in which we indent successive columns by one increment. And we go all the way to the bottom row. then if we perform Gauss elimination on this matrix, you would find that the top row would be unchanged. The second row would be 0, 1, 2, and then the last row would be all zeros. And so these both have the same rank. So while the determinant, well, it's easy to see that the determinant of this matrix is 0, because we'd be multiplying every term by a 0 when we calculate the determinant. And so the rank here turns out to be equals 2. So the rank of both matrices is equal to 2. And this finally leads us to the last theorem, which is theorem 10.5.2. And that states that for any matrix A, the number of linearly independent rows, which, as you recall, is the dimensionality of the row space, that is, the number of linearly independent rows describes the span of the rows, and it's the same as the dimensionality of the row space, and the number of linear independent columns, or the dimensionality of the column space, are the same. So the number of linearly independent rows is equal to the number of linearly independent columns. And the values, or those numbers, give the rank. So the rank of A is equal to the number of linearly independent rows and the number of linearly independent columns. So the easiest way to compute the rank to determine the rank of A is to count the number of linearly independent rows or columns. So if you see two rows that are linearly related to each other, or two columns that are linearly related to each other, you know that factors into the number of linearly independent rows or columns. But if you can't do that by just looking at the rows, so if you can't do that by first inspection, then you should reduce the matrix by Gaussian elimination or Gauss-Jordan reduction, but Gaussian elimination should be sufficient. And the rank is the number of non-zero rows at the bottom of your reduced matrix. And the reason you can do that is I'll tell you now that any zero row or vector is linearly dependent on other rows or vectors. And the way you could tell that is, for example, if you have one row that you multiply by alpha 1 and you add that to alpha 2 times a zero row and set that equal to 0, alpha 2 need not equal 0 to solve this equation. So that tells you that there's a linear dependence between this non-zero row and the 0 row. Okay, so this is in practice a relatively simple way to determine the rank after going through these three theorems. And the rank is a very important property of a matrix, and we'll go into reasons why it's important in some applications in the next few videos.